These are the solutions to the numericals given in internal test 1 of physical chemistry T.Y.B.Sc. The first question says the first order reaction is 50% complete in half an hour at 27 degrees centigrade and 10 minutes at 47 degrees centigrade, and we are supposed to calculate the energy of activation. So let's write down what is given. T half 1 is zero point 0.5 hours, which is 30 minutes. T half 2 is 10 minutes. T1 is 27 degrees centigrade. When converted into Kelvin, it is 300 Kelvin, and T2 is 47 Kelvin. 47 degrees centigrade, it is 320 Kelvin. For a first order reaction, T half is given as 0.693 divided by K, where K is the rate constant. So T half 1 is 0.693 by K1, and T half 2 is, the Arrhenius equation is in this form. Now if you substitute the value of K2 here, so K2 would be 0.693 upon T1 T half 2, and K1 would be 0.693 divided by T1 half. Substituting the value of K1 and K2, we can see that this equation becomes log of T half 1 divided by T half 2, and right hand side is the same. So let's substitute log of 30 by 10, energy of activation. I put the value of R as 1.987 because I'm going to write the answer of energy of activation in calories. T2 minus T1, T1 into T2. Solving this, the solution is 10479.87 calories per mole. Let's read the second question. This is, most of the students have done this wrong. What are given? First, the reaction is a first order reaction, and half-life is given as 35 minutes. But so from half-life, of course, we can calculate the value of rate constant. But that rate constant will be at 153 Kelvin. And the question is, what is the time required for 40% completion of the reaction at another temperature? Which means the K that we find from here cannot be used to find out the time required for 40% completion at this temperature. So this is the roadmap for this numerical. So first, from this T half, because it's a first order reaction, we are going to calculate the value of K. That K rate constant value will be at 153 Kelvin or 426 123 degrees centigrade or 426 Kelvin. But we need K value at minus 73 degrees centigrade or 200 Kelvin. So using Arrhenius equation, assuming that this is the value that we find from here is K1, this is T1, we'll find out the value of K2 at this T2. And once I find out the value of K at this temperature, rest of the numerical is fairly simple. So let's solve it. So T half is given at 153 degrees centigrade is this much. So K value at this temperature is 0.0198 per minute because we have taken the time in minute. Now this is the temperature T1. So T1 is 153 degrees centigrade, which is 426 Kelvin. T2, we need to find out the K value at this temperature. So T2 is minus 73 plus 273 is 200 Kelvin. Energy of activation is given. We removed calorie by multiplying by 1000. So this is K1. We need to find out K2. This is T1 and this is the value of T2. Now putting this in Arrhenius equation, so log of K2 divided by 0.198. Energy of activation is this value 2.303. R value is 1.987 because energy of activation is in calorie. T2 over here is 200. So it is 200 minus 426. Then 426 multiplied by 200. Obviously, this number is smaller than this number. So this entire right hand side, when you solve it, it is going to come as a negative value. So log of K2 0.0198 is equal to minus 5.432. So if it, because since this log is log to the base 10, so K2 upon 0.0198 would be 10 raised to minus this value. Solving this with the help of a calculator, this value comes out to be 3.76, 3.7 into 10 raised to minus 3. So K2 will be this number multiplied by 0.0198, which is 7.33 into 10 raised to minus 8 per minute, because K1 was in per minute. Having found K, now this value of K is for this reaction at temperature minus 73 degrees centigrade. Please keep this in mind. So we're going to solve the second part of this numerical. So this is the K value at that temperature. We want 40% completion of the reaction, which means if we start with 100 A, 100 reactant, 40% would have been 40 would have been converted into the product. So the reactant remaining would be 60, and we need to find out the time. So K1 is equal to, this is the first order equation. K value, this is the value that we put at temperature minus 73 degrees centigrade. This is the same by T. We're going to find out T. Since K1 is in per minute, whatever answer we get for T time is going to be in minutes. Log of 100 divided by 60. So the solution is T is equal to 6.975 into 10 raised to 6 minute. Question number 3. Arrhenius pre-exponential factor A is given as this. Energy of activation is given to be this much. Calculate. We have to calculate at what temperature the rate constant is 4.32 into 10 raised to minus 5 per second. Putting this in the Arrhenius equation, K is equal to A e raised to minus e raised to minus EA by RT. So this is the value of K, this is the value of A, e raised to minus energy of activation has been converted into calories by multiplying by 1000. R is 1.987 and T. We have to find out the value of T. So this thing will come this side. So 4.32 divided by this is equal to this much. Solving this, so we have the solution of this part will become 7.082 into 10 raised to minus 19 is equal to this much. So when you take this, this will be log to the base E. So ln of this much is equal to minus this. So T will be this minus this divided by log of this. So T is given to be 164.62 Kelvin. Question number 4. The resistance for this concentration of KCl is given to be this much. Its specific conductance is given here. So resistance for KCl is given, specific conductance is given. We find out the cell constant. Cell constant is equal to resistance multiplied by specific conductance. So it is 117.03. The same cell is used, which means the cell constant, we can use the same value of cell constant. This the resistance is 220 ohms. For a decinormal solution, decinormal means 0.1 normal, we have to calculate the equivalent conductance. So for equivalent conductance, we need the specific conductance. So specific conductance of the solution is cell constant divided by R. Cell constant comes from here. R is 220. So that specific conductance value is this much. Then we have to find out the equivalent conductance, which is Ls into 1000 divided by C. C is decinormal, so we'll substitute the value of Ls as this. 1000 comes here, C will be 0.1. Solving this equation, the answer is 5.32 ohm inverse centimeter square gram equivalent inverse. Fifth question. This is a question based on Colruyt law. You've been given the equivalent conductance of at infinite dilution for three salts: ammonium chloride, sodium hydroxide, and sodium chloride, all strong electrolytes. So let's write down the given. This is for ammonium chloride, this for NaOH, this for NaCl. Using Colruyt law, equivalent conductance at infinite dilution for ammonium hydroxide will be ammonium chloride plus sodium hydroxide minus NaCl. Substituting the value of this, we get the equivalent conductance of ammonium hydroxide at infinite dilution to be 2.38.3. We need to find, we have been given that the equivalent conductance at this particular concentration is this much. So degree of dissociation is given as lambda divided by lambda naught. So it is 11.45 divided by 238, which will come to 0.048. This degree of dissociation, so this is dimensionless, this has no unit. And the last question, find out the equivalent conductance and specific conductance. So we have to find lambda and Ls for NaCl. Concentration is given as 5 into 10 raised to minus 2 normal. This is the cell constant, and resistance is given. So cell constant is given, concentration is given, resistance is given. We have to find out specific conductance and equivalent conductance. Let's find out the specific conductance first. Specific conductance is cell constant divided by R resistance, so 0.68 divided by 1130, so it becomes 6.02 into 10 raised to minus 4 ohm inverse centimeter inverse. Equivalent conductance is Ls 1000 divided by C. So Ls comes from here 1000 and C is 5 into 10 raised to minus 2. So answer is 12.04 ohm inverse centimeter square gram equivalent inverse. I hope this most of you did this correct. Thank you very much.